Welcome back to part 2 of gas chromatography. Dear student, in part 1 we have studied the basic principle of gas chromatography, the advantages and limitations of gas chromatography, then the component of chromatographic instrument, that is first component we were discussing, that is carrier gas. Now, with this lecture, we'll continue with the instrumentation part. The second component is your sample injection devices. So either we are having direct sample injection, which is mostly used using this hypodermic syringes or needle, or we are having the automatic sampler injectors or headspace sampling injectors. In new instrument, we are having purge and trap sample injectors or pyrolysis sample injector, where the sample is to be introduced by the pyrolysis of your material. The direct injection system utilizes the hypodermic syringes which are introduced through the sample injection ports. So these are the self-sealing rubber septum which are situated with the sample injection port, and they are provided with the sleeves. The sleeves are available in two types. One is called as a split or another is called as a splitlets. The split sleeves are available where a small quantity of sample is allowed to enter and the rest of the sample is retained into the sleeves. And splitless, every part of the sample which you are entering is entering into the column. So there are two types, split and splitlet systems. So the injection port purpose is to vaporize the sample. It is kept 50 degrees centigrade more heater than your oven temperature. So as soon as you inject the sample, it will be vaporized here and converted to a sample plug. Then it transfers the sample to the column with accuracy and the reproducibility. So we can handle gaseous samples or liquid samples using these sample injection ports. So I will show you one examples of sample injections. So this is the hypodermic syringes and needles, Helminton type syringes, which is up to the 25 microliter sizes are used. Variable sizes are available, 5 microliter, 10 microliter, 25 microliter. So they are used. So there is a protector to prevent the damage to your plunger. Only 2 to 5 microliter of sample is required to be injected into the column, which means that you fill only a small part of the barrel with the sample. So before you inject the samples, you have to see the marking on the syringes, because it is marked either for 5 microliter, 10 microliter, 15 microliter, 20 microliter or 25 microliter. You have to just see the list count of your syringes which you are using for injection of the sample. The second very important component of your gas chromatography is the columns. The mixture separation take place into the columns only. The most important part of GC may be made up of its glass or stainless steel. It is classified as analytical column or preparative column, depending upon type of use, whether we are separating or we are separating and using it for the further purpose. It can be also classified as a capillary column or packed column. Capillary columns, many books says it as a open tubular columns. So in some books, it is called as a wall coated or support coated columns. So these are the capillary columns and these are the packed column which are used in the gas chromatography. So two types are used in gas chromatography, that is packed column. They are generally 1.5 to 10 meter in length and have an internal diameter of 2 to 4 mm. This tubing is usually made up of the stainless steel or glass. It contains packing of finely divided inert solid support material, that is diatomic earth material, that is coated with liquid or solid stationary phase depending upon partition chromatography or adsorption chromatography. The another is your open tubular columns, generally called as a capillary column, having very small internal diameter on the order of a few tenths of millimeters and length between 25 to 60 meters are used. The inner column walls are coated with active materials, so they are called as a wall coated open tubular collar watt column. Some columns are quasi-solid filled, which may parallel micropores materials are there. that is called as a plot columns, which uses this material on which a thin film of liquid is to be held, and this material is coated on surface of this column. These columns are flexible, so every long column can wound into a small coil and it can be incorporated into the instruments. See this porous layer open tubular column that is called as a plot column. So they are having a thin layer on the surface of column which is holding the liquid on their surfaces. Therefore, they are called as a plot column. Their particle layer thickness is between 5 to 50 micrometers and tube ID is 320 to 530 micrometers internal diameter. Then these are the packed column. The packed column, the adsorbent are filled, which are directly acting as a stationary phase, or the packed column holds the liquid, which can act as a stationary phase. The internal diameter is less than 1 mm. Generally, we are using capillary columns. They are called as a wall-coated open tubular column, and these are called as a plot column or support-coated open tubular columns, COT columns. So we are using what column? What WCOT columns. So these WCOT columns holds film directly into the internal part of the glass tubings. The film thickness is between zero point 0.1 to zero point 0.8 mm and the tube internal diameter is from 100 to 530 micrometers. The various stationary phase used in gas chromatography are listed in this table. So they are trade names are written here. OB1, AC30. So they are polymethyl siloxane columns, general purpose column. They are non-polar phases, hydrocarbons, polynucleic aromatic compounds, drugs, steroids can be separated and they are working at 350 degrees centigrade. Some are called as OV3, AC50 through 52 columns. They are polymethyl dimethyl siloxane 30% phenyl columns. They are useful for fatty acids, methyl esters, alkaloids, drugs, halogenated compounds, and they are to be working at 350 degrees centigrade. The OV70 columns are used for drugs, steroids, pesticides, and glycols. So they are polysiloxane, that is 50% phenyl columns. Then some are OV210. They are polytrifluoropropyl dimethyl siloxanone derivatives, which is to be carried out at 200 degrees centigrade and specifically for chlorinated aromatics, nitroaromatics, alkyl substituted benzenes. So for that purpose, this type of the columns are utilized. Carbovax 20M, these are the common column for free acids, alcohol, esters, essential oils, and glycol separations, which are working at 250 degrees centigrade and having the stationary phase of polyethylene glycol. Then OV275, it is a cyanoalyl dimethyl siloxane, which is working at 240 degrees centigrade, used for the separation of polysulfonated fatty acid, rosins, acids, free acids, and alcohols. Now, preparation of column. Preparation of column is a very tedious part in the column chromatography. Equilibration of column. The packed columns are equilibrated before introduction of the sample. This is done by allowing continuous flow of heated carrier gas through the column for a specific duration time, generally 24 hours at prescribed temperature, and continuous flow of carrier gas is allowed during this period. Ideally, prepared and conditioned column shows zero baseline on the recorder upon passing of the carrier gas alone. The column temperature is a very critical one. This can be controlled by electrically heated metal blocks or circulating air baths. The compounds of low boiling eluted at low temperature. Compounds of high boiling materials boils at a higher temperature, resulting in broader and shallower peak requiring temperature programming. So the column ovens which are uses are provided with the programming temperature facility. The column is contained in a heated oven that is processed by heated injector port and followed by a heated detector unit which produces the output. A set of program parameters regulates the operation of the system. Two operations are available, either isothermal programming, that is same temperature throughout the process, or linear programming where we can program to change the temperature during process of separation, that is linear programming. So this temperature programming that is called as a PTGC, they uses a column with the temperature is rise slowly during the process of elution and the vapor pressure of analytes increases which eluted faster. You can see the examples. If you are carrying out the elution at isochromatic temperature, isothermal conditions, the resolution and the retention time is very long. So as you go for the gradient elution, the retention time also decreases and more resolved peaks you will get. So rise column temperature during separation, temperature programming separates species with wide range of um, polarities or vapor pressure. The next component is a detector. After the component of mixture are separated using gas chromatography, they must be detected as they exit the GC columns. The detectors can be grouped into concentration dependent detectors and mass flow dependent detector. The signal from the concentration dependent detector is related to the concentration of solute in the detector and does not usually destroy the samples. Dilution with weak makeup gas will lower the detector's response. So they are called as a bulk sensing detector. So whatever bulk entering into the column, they get detected by this type of the detectors. Thermal conductivity detector is examples of such type of the detectors. The second is a mass flow dependent detector. Usually destroy the sample and the signal is related to the rate at which solid molecules enters the detector. This includes your flame ionization detector or electron capture detector. The response of mass flow dependent detector is unaffected by makeup gas which is used in the gas chromatography. The type of detectors which are used in gas chromatography include thermal conductivity detector, flame ionization detector, electron capture detector, nitrogen phosphorus detector, flame photometric detector, pulse discharge detector, and mass selective detector, that is mass spectrophotometer as a detector. We'll see few examples of this detector. The first one is your flame ionization detector. But before that, we'll see the ideal detector properties. The ideal detector properties include adequate sensitivity, that is slope of the response curve should be linear with the detector. So it should have the good stability and reproducibility, a linear dynamic range that expands over several order of magnitude can be used, a temperature range from room temperature to at least 400 degrees centigrade, the detector should give the linear response. A short response time that is independent of the flow rate is important characteristic of ideal detector. It should be stable and highly reproducible and easy to use. A predetectable response towards all solutes is important part. Non-destructive to the samples when the sample is precious and costly. It should have the good sensitivity, that is 10 raised to minus 8 to 10 raised to minus 15 grams of solute per second, and it should produce uniform response to all analyte. The first detector is your flame ionization detector. It operates by principle that by change in conductivity of the flame as the component is burned. So ionization will take place due to the thermal energies. The change in conductivity of the flame does not arise by sample ionization of compound. It is partial or complete stripping of the compounds to give charged hydrogen, defined polymers or aggregates of carbons of low ionization potential. See the diagram? You can see there is a flame. Generally, flame is produced by using the hydrogen, and the sample when enters will get ionized, liberating the electrons which are captured by these plates. These are called as a collector assembly, which will captures all these ions and they will be converted into the electrical signal. Then this is the air in for supporting the combustion of your hydrogen gases, and exit from the column is entering through this nozzle in the flame. So it is a rugged, it is sensitive up to 10 raised to minus 13 grams per second. It is wide dynamic range. Signal depends upon the atoms in organic analytes, carbon atoms in the organic analyte. It is a mass sensitive, not the concentration sensitive. It is weakly sensitive to the carbonyl, amine, alcohol amine groups. Cannot be used for the water, carbon dioxide, sulfur dioxide. So it is destructive also. The second detector which is used is thermal conductivity detector called as a TCD. It is based upon alteration of thermal conductivity of the carrier gas in presence of an organic compound. The platinum wires are heated electrically and assume equilibrium conditions of temperature and resistance when carrier gas along passes over them. So this is the block where there are the four cells. Two cells are used for the sample and two cells are used for the references. They are mounted in Wheatstone bridge arrangement, and when compound emerges, the thermal conductivity of gas surrounding wire alters, and hence the temperature and resistance of wire changes with a uh, concomitant out of a balanced signal which is amplified and recorded. So as soon as your sample will enter into this sample compartment, the bridge will be in balance, and it is to be balanced by applying external current, and how much current applied will be equals to the amount of substance which is entering into the sample compartment. It is rugged. Wide dynamic ranges can be separated by using thermal conductivity. It is non-destructive in nature, but it has a less sensitivity as compared to your flame ionization detector. It is insensitive, and it is non-uniform. The third detectors, which is commonly used in gas chromatography, is electron capture detector called as the ECD. The ECD ionizes the carrier gas by means of a radioactive sources. The potential across the two electrodes is adjusted to collect all ions, and a steady situation current is therefore recorded. So in case of flame ionization, the ionization is carried out by using the hydrogen flame. Here the ionization is carried out by bombardment of the electrons from a radioactive species like your nickel. So this is nickel 63 as a source. It is used here, and when the sample enters from your column, it will get ionized here. The ions are collected by the electrode which is placed in the part, and this is the effluent out. So electrons from B source ionizes carrier molecule, captures electrons and decreases the current. Samples, it is simple and reliable. It is having also the good sensitivity to electronegative groups. Basically, it is used for detection of the halogens and peroxides. It is this limitations also. Largely, it is non-destructive, but it is insensitive to amines, alcohols, and hydrocarbons, and have the limited dynamic range to chlorinated compounds only. halogenated or chlorinated compound. So it is used for detection of pesticides. Evaluation in GC. The last part of your GC is the GC chromatogram. You can see how to do your read a chromatogram and what does it tell you. You can see on the graph it is a plot of retention time or time versus response. In case of this, we are just determining the retention time of your sample. Okay, so we are determining the peak width. So this is called as a peak width, which is determined to maintain the similarity between the two parts of your peak. Okay, we'll see this theory in the next video, but we'll see what to learn, what to see in from the graph. Okay, so this is a qualitative part that retention time will tell you what type of a substance is there, and for quantitative determinations we are measuring the peak which is covered in the area which is covered in the peak and the peak height that denotes the concentration, so it can be used for the quantitative purpose. Each component of mixture reaches the detector at a different time and produces a signal at characteristic time called a retention time that we are measuring in your gas chromatographic chromatogram. The area under a peak is related to the amount of that component present in the mixture. So here I will stop the second video and I will meet you in the third video where I can explain you the theoretical aspect of gas chromatography. Thank you and see you in the next video.